Okay, let's talk about pitch class sets. And here is the handout, pitch class sets basics or essentials, pitch class set theory essentials. And you also presumably have done the reading from the Dr. Hicks packet, which explains a lot of things. One thing we should say is that this theory is actually more straightforward than tonal theory, to be honest. It's kind of dumber in a way. It presupposes the 12-tone equal tempered system, whereby the octave is divided essentially into 12 equal half steps, which was not how the tonal system developed. It's more based on unequal half steps, or half steps that result from more basic intervals. Anyway, but we start with the concept that the octave is equivalent and it's divided up into 12 equal half steps. Octave equivalency, thus we get this concept of pitch class. And you'll notice here, what is pitch class? What's the difference between pitch class and pitch? Well, these 4 notes, they're different notes, and these 3 are different pitches, but they are the same pitch class. So if we go over to the piano, we'll notice that we actually have 7 notes of the pitch class C. 4, 5, 6, no, it's 7 or 8, I don't remember. Anyway, those are 7 different pitches, but the same pitch class. And even if we call this a C or a B sharp or a D double flat, heaven forbid, this is still the same pitch class. Okay, so we need to remember that distinction between pitch and pitch class. Let's go to the next item on this handout, which is right here. We have this interval. And we have 4 different ways of describing intervals. Now, I can guarantee you something like this might be on your first test. Each of these ways of describing intervals is important for different reasons. We remember in the tonal system, we had 2 different ways of describing this interval. Again, pardon the out-of-tuneness of my piano. This could either be a perfect 12th or a perfect fifth, or a compound perfect fifth. Okay, so that's our traditional designation. And then we have our pitch interval, and this gets into atonal theory. And in atonal theory, instead of having different kinds of seconds, thirds, fourths, fifths, sixths, and sevenths and octaves, we simplify it and we simply count semitones or half steps. The word semitone is the same as a half step. We count them, just like if you had a guitar and you count frets. I used to play, punk bands with people that had no musical knowledge, and they would count frets. Is it 4th fret, 6th fret, whatever. Guitarists will know about that. That's how we count intervals in atonal theory. So, to get the exact pitch interval between C4 and G5, we count the semitones. But again, the keyboard is useful for this. Let's have a look. We start here and we go to here. So there we're going to go 1, and we don't count the first one like we do with tonal intervals, which is weird, but we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So in other words, this interval is 19 semitones. Okay, so that's a pitch interval. Okay, so we've got our tonal interval, perfect 12th or perfect fifth, then our pitch interval, then we have our pitch class interval. And that is very similar to like getting the perfect fifth out of the perfect 12th. We're going to erase any intervening octaves. Now an octave in pitch class intervals is 12 semitones. Okay, so we subtract 12 from 19, and that gives us 7. Okay, and that indicates that we're still moving in that direction. We're ascending from this C up to this G minus one or more octaves. So that's the pitch class interval. Okay? Here we can look at it here. We've got, instead of going from here to here, we'll take that down an octave. Okay, and then we have 1, 2, 3, 4, 5, 6, 7. Perfect fifths always have 7 semitones. You're going to get used to that. Okay, then we have one further abstraction of this interval, and that is the interval class. And this term, interval class, is an important one. Pitch class set theory, of course, borrows from basic algebraic terminology and uses very simple numbers. And we have we have 6 interval classes total. And that's what you've got over here. A total of 6 interval classes. Interval class 1 includes minor seconds and major sevenths, or their compounds and harmonic equivalents. Compounds being, you know, a minor second or minor ninth, or those are all, or the major seventh. Those are all interval class 1. Then the second interval class 2, includes major seconds. Okay, I'll show you. Major seconds, minor sevenths, right? And any of their compounds, in other words, this or this, or this, or this. Okay, and any of their enharmonic equivalents, in other words, C to B flat or C to A sharp. You remember with tonal intervals, a C to B flat would be a minor second, a C to A sharp would be an augmented sixth, which we actually used a fair amount. You remember French sixth has an augmented sixth in it. Well, there's no difference between an augmented sixth and a minor seventh in atonal theory. They're both 10 semitones, but they also belong to this interval class of 2, interval class 2, which includes the tonal intervals 2 and 10. Then we have minor thirds, interval class 3, which includes minor thirds, major sixth, their compounds and enharmonic equivalents. In other words, 3 semitones. And the major sixth, which if I rotate it, I take that note, put it down an octave, it turns into a minor third. Well, in other words, interval class, this concept, recognizes inverted intervals as being equivalent or belonging to the same class. Okay? Doesn't mean they're exactly the same. It means they have an equivalency, an area in which they are equivalent. Then we have interval class 4, major thirds, minor sixth. Okay? So in other words, 4. And another way to look at this is 12 minus 4, an octave minus 4, which is 8. So that's another way to look at this. I should have written this in, but interval class 1 contains 11, interval class 2 contains 10, interval class 3 contains 9, 4 contains 8, etc., 7. Now, we'll talk about that in a minute. Anyway, so this interval class, it's a type of abstraction of intervals into these classes. The one that's unusual is, of course, interval class 6, which is the tritone. Of course, we remember that the tritone inverts to itself. We remember that from the beginning of Purple Haze, if you know that. But anyway, so those are the 6 interval classes. I suppose we could have an interval class 0 that includes 0 and 12 and its compounds, but those aren't included in, well, there it is, interval class 0, the unison or octave. Okay, so these interval classes are going to be important. Just keep them in mind. It's a way of abstracting the concept of interval further. Now, the other concept that's not laid out clearly here, we'll all laid out here. Okay, we think of like a clock face, which you're hopefully all familiar with. Of course, we have a 12, 3, 6, and 9. Well, it's very convenient that we can use this idea, and then of course 1, 2, 4, 5, 7, 8, 10, 11. We have 12 pitch classes, and if, let's say we start at C, and we call C 0, 1 is C sharp, 2 is D, 3 is E flat, 4 is E, 5 is F, 6 is F sharp, 7 is G, 8 is A flat, 9 is A, 10 is B flat, 11 is B, and then we get back to C, okay? This is what's called modular arithmetic, and more specifically, mod 12 arithmetic. And we do it all the time. For instance, if it's 11 a.m. and you say to someone, well, I'll see you in 3 hours, we know that that's 2. 11 plus 3 doesn't equal 14, it equals 2. Because what we do in our minds is we say, well, 11 plus 3 actually equals 14, but then we subtract 14 minus 12 equals 2. That's what we do. We always subtract 12 from any number above 12 to get our actual number. We do the same thing in pitch class set theory. We're only dealing with 12 pitch classes. So let's say we've chosen, and when we're doing pitch class set theory, we can either choose C to PR0, or we can choose another pitch class to BR0. But once we choose something to BR0, and let's say it's C, if we say that, let's say G, which is 7, plus 8, okay, and an 8 is a minor sixth, by the way. 7 plus 8, of course, equals 15. Okay, but then 15 minus 12 equals 3. Okay, well, we could say, again, that this is G, and then 3 is E flat. So if we go up a minor sixth from, which is this, from G, that does go to E flat. Here, I'll show you. Okay, here's G. Okay, C is 0, that C is also 0 or 12. We go up 8 semitones, 1, 2, 3, 4, 5, 6, 7, 8. Okay. Well, that's 15, 12, 13, 14, 15, but we subtract 12, in other words, the octave, and then we get 3. 0, 1, 2, 3. Okay, so that's a little example to give you an idea of how modular arithmetic works. We'll talk more about this. It'll become clearer as we go along. So that's a basic concept, mod 12 arithmetic. Now let's continue with our little discussion. Okay, so that enables us to describe the relationship between any pitches or any pitch classes. And we've got, like I said, 4 different ways of describing that, but we're most interested probably in the pitch class interval and secondarily the interval class. Okay, those are the two ones that we're most interested in. So any relationship between two notes can be described using the number of semitones, especially the number of semitones minus any octaves that intervene. So for instance, if I go like this, okay, E flat to this D flat, well, let's bring this down an octave. And we've got, I'll show you, sorry. So initially we have this up to here, E flat up to D flat. Let's bring this D flat down an octave. as we did with tonal intervals. Then we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 semitones. That used to be a minor seventh, but we're going to make it even simpler and just call it semitones. Now, if we invert this, if we want to say what's the shortest distance between the pitch class E flat and D flat, well, if we want that, then we do what's called rotating. We don't call it inverting. We rotate. In other words, we move this down an octave to here, and then that gives us 2 semitones, which is actually the interval class of 10 semitones. Okay, let's do a little more work here. Now, okay, so that gives us a way of describing the relationship between 2 pitches or 2 pitch classes. What about more than 2? Okay, I'm glad you asked that. Well, we have, that's where we get into pitch class sets. Now, what is a pitch class set? Well, here's a pitch class set, E, C, and D sharp. Now, a pitch class set is a sort of an abstract collection of pitch classes. And you remember there are only 12 pitch classes. So a pitch class set doesn't care who's, about octave placement at all, or context, whether it's a chord or whether it's a part of a melody. And this gets us into another concept of Schoenberg's that's kind of important, which is the unity of musical space. Let's write that down. Unity of musical space. Now, what does that mean? Well, it's simpler than it sounds, but again, we talked in the last lecture about the concept of relativity. And Schoenberg was very excited about this idea that pitches and notes didn't have to be grounded to a tonality, and that even extended to the rhythmic realm, where he kind of tried to problematize the downbeat and the hierarchical parts of a measure and really try to defeat that sensation. But that also manifests itself in this concept of the unity of musical space. Unity of musical space means that melodic entities and harmonic entities are drawn from the same materials. So if you remember in tonal music, that is not necessarily the case. Melodies are mostly made out of steps, major and minor seconds, maybe augmented seconds sometimes. So, if we think of the most extreme example of this, like Beethoven's Ode to Joy. Only stepwise, of course, most melodies have some skips, but they're mostly steps with a few skips here and there. Again, this is in common practice music. This starts to change in the 20th century. So, melodies made out of steps. Harmonies, what are those mostly made out of in tonal music? Well, they're mostly made out of thirds. And even if we go further, the triad, 2/3, the seventh chord is 3/3. So, in tonal music, harmony, building blocks are thirds. Melody, the building blocks are seconds. Well, in the atonal music, unity of musical space, harmony and melody made out of the same materials. That's why instead of talking about scales in reference to melody and chords in reference to harmony or something of that sort, we talk about the same materials, the same pitch class collections as being used in both melody and harmony. Now let's look at a little bit about how this is manifest. So we've got, in other words, let's say we take this set of pitch classes, E, C sharp, C, and D sharp, which in this case is here. Well, that could be used as a chord, or it could be used in a melody, etc. I mean, that's basically what we're going to find in Schoenberg's, or it could be used as a little both. Combination of the two. Okay, so here are some basic operations of how to vary a pitch class set. In this case, pitch class set consisting of these 3 pitch classes. We could take the close spaced version of this pitch class set and rotate it by changing the order in pitch space. Moving this E up an octave. There's a new one. We could move the C up an octave. So those are two different rotations, but they're still the same pitch class set because they contain E, C, and D sharp. Now we could call the D sharp and E flat. It would still be the same pitch class set because E flat and D sharp are equivalent in atonal theory. Then we could also use open-spaced versions of the same pitch class set. We could also include octaves and even a bigger version of it. Let's see, I'm going to need. Okay, those are all versions of this pitch class set, E, C, D sharp. It's pretty straightforward. We're familiar with this with tonal music. We have a C major triad. These are all versions of the C major triad. C, E, G is a pitch class set. Okay, now then we get into this this concept of normal order. Well, what is normal order? Well, to get the normal order of any pitch class set, we take all the close-spaced versions of that pitch class set. There are only 3 with a trichord. Okay, so pitch class sets are defined by their cardinality, or the number of pitch classes in them, or the number of elements, if we think of set theory. So a trichord has 3, tetrachord has 4, pentachord has 5, hexachord has 6, heptachord has 7, octachord 8, nonachord 9, decachord, I don't remember the other ones. But anyway, we mostly deal with trichords, tetrachords, and then maybe hexachords we deal with, pentachords a little bit. But mostly trichords are the one we're going to focus on the most. There are going to be 3 different close-spaced versions of a trichord. The normal order is which of these 3 has the smallest distance, is the most compact. Okay? Now, obviously that's this one. This is so far the normal order. Now, occasionally you'll get especially with well, we'll come to this, but occasionally you'll get versions of the same chord that have the same interval between the top and the bottom note. Then you want to say, well, which one has the smallest interval between the bottom and the next note up? And that's going to be the normal order. Now, what we're doing right now, trying to figure out normal order, is we're basically trying to, we're creating a classification system. There's nothing aesthetic or essential about normal order. It's simply, like I said, it's a construct. It's a way of abstracting a collection of pitch class sets. And this is found to be useful in digesting this music, to say, okay, here's a bunch of chords like these ones, and they all belong together in a class or a category. And how do we define that class or category? Well, this is the way that Alan Fort, the theorist that I mentioned earlier, came up with. He said, first of all, let's find the normal order. Okay, so this is the normal order of so far. Well, then we get into another idea, which is another way to vary a chord, and you'll notice over here it's inversion. Okay, so what is inversion? Well, this means that we take, let's do it at the keyboard first. It's different from inversion in tonal music, which we're calling rotation. So in other words, if I take this chord and we go like that, we call that inversion in tonal music. Now we call it rotation, taking that C, moving it up an octave. Inversion is quite different. Inversion, so we ended up with this C, D sharp, E is our chord. Well, what if we take this guy and we do the same intervals going down instead of going up? We invert around this axis of C. So instead of going up 3 semitones and up 1 semitone, we're going to go down 3 semitones and down 1 semitone. So this is the inversion of that. Okay? Now, well, let's just leave it at that. It's a little more complex than that, but for now, we'll leave it at that. So let's look at this in terms of notation. In which case, we're gonna say that that inverts to this. Again, spellings don't matter. I mean, this could be an A flat. It doesn't matter in atonal music. So that's the inversion of that. Now, why am I bringing this up? Well, in atonal theory, acknowledging that Schoenberg loved the idea of inverting collections of pitch classes as being somehow equivalent, in atonal theory, in pitch class set theory, inversion, chords that are related in this way are considered equivalent. Now, we should draw a distinction between equivalency and identity. So, identity, saying two things are identical means that they're the same in every respect. Saying that two things are equivalent is generally perceived to be more qualified, equivalency in a particular respect. So, in this system of pitch class set theory, inversion of this kind says that these two pitch class sets are belong to the same set class. So that takes us to the concept of set class. Okay? And so we'll talk about that in a minute. But these two chords are considered to be equivalent in some way. They belong to the same set class. Again, we talked about interval class, 6 interval classes. Well, we're talking about pitch class sets, and each pitch class set belongs to a set class. And that's the chart, the Alan Fort chart that will become your best friend, is a listing of set classes. And that's mainly what we're going to be dealing with in this class. Well, I'm using the word class a lot. Okay, so there's normal order and then there's prime form, which is somewhat the same as best normal order. But I would bracket that and think in terms of prime form. So we've got normal order, and then we've got a further abstraction, prime form. So the difference between these two is normal order is what's the most compact version of a pitch class set. And if we have two different versions that are the same distance between the top and the bottom notes, then we choose the one where the second note is closest to the bottom, and if that's the same, then the third note, etc. When we get into the bigger pitch class sets, we might get this situation where we have all these tiebreakers, but we won't worry too much about that. Then we say, okay, we've done that. Let's look at the normal order and the inversion of the normal order, and let's see between those two which pitch class set is most compact toward the bottom, okay? Which is has the notes closest to the bottom note. Another way to look at it is we're going to start using our numbers, okay? And we already learned how to count intervals. Well, now we're going to go a little bit further, and we're going to use a little parentheses. We're going to call the bottom note 0. We can use commas if we want, or we can leave them out. And then we're going to count up from A to D sharp. C. C up to D sharp. C, 1, 2, 3. So C is 0. D sharp is 3. And then E is 4, counting from the C. Again, if we choose C to be our 0, then it's even easier. So that's 0, 3, 4. But in this case, we're just going to use whatever the bottom note is, we're going to call that 0. So in this case, we're going to say the G sharp is 0. That means the A is going to be 1, and the C is going to be 4. So G sharp, A, C. We don't care about the order. Again, this is unity of musical space, relativity, you know, we're going to... We could also count from the top and go 0, 1, 4. Count in the opposite direction, which would be consistent, again, with this theory. But anyway, 0, 1, 4. And then we want to say, well, which of these two things is most compact toward the 0? Of course, it's 0, 1, 4. Another way to do it is if we add up the elements of this set or that set, which one has this lowest sum. Of course, this one, 0 plus 1 plus 4 is 5. This one is 7. So that's going to be, so that's how we determine the prime form is. We take a normal order pitch class set, we abstract it down to these numbers with 0 at the bottom, and then we invert it and compare and see which of the two ends up being the prime form. Okay, let's talk about set class. I've discussed it here. A set class is an abstract representation of the intervals in a pitch class and its intervals in a pitch class set, that should say, and its inversion. A set class includes up to 24 members, i.e. pitch class sets that belong to that set class. So let's look at that a little bit closer. Here is your marvelous, well, and I should mention, here's all rotations, voicings, transpositions, and inversions are members of a set class that is represented by the numerical representation, in this case 0, 1, 4, which we call the prime form. There are up to 24 unique members of each set class. So the 0, 1, 4, which is 0, 1, 4, I'll show you here, 0, 1, 4, but that could include this, this. Okay, there are 12 of those, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, and then we start over again. But also, you remember that a set class also includes its inversion. 0, 1, 4, 0, 1, 4, which is different from this, but they're equivalent under pitch class set theory. So there are 12 of those. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 before they start over again. So every set class has 24 members. Now again, this is the concept of pitch class, not pitch. So obviously, this pitch class set, you know, let's say here, E flat, F sharp, C. Well, I could, you know, that's not the best version of it. I could have it. There's a kind of a nice same. Just by using octave displacements, I've created actually a kind of pretty chord. So again, it's not talking about pitch, it's talking about pitch class. And therefore, through transposition, inversion, and octave displacement, I can get any of these chords from the 0, 1, 4 set class. So for instance, I'll play some of these for you. You know, they all have kind of a different sound. Different, but the same. You know what I'm saying? So, okay, meaning they have something in common. Now this is important because what we call the second Viennese school, and I didn't mention this before, but Arnold Schoenberg, with his two main students, Anton Webern and Alban Berg, the three of them form what's called the second Viennese school. Well, you can imagine what the first Viennese school was. That was Haydn, Mozart, and Beethoven. And of course, they were similar in that Haydn was certainly a formal teacher of Beethoven. He was also sort of a mentor to Mozart. So they were the first Viennese school, and then Schoenberg, Webern, and Berg were the second Viennese school. Well, they loved this particular trichord, the 014 trichord, which we actually end up calling the atonal trichord, because it's one trichord that cannot be found in the diatonic collection, the white keys of the piano, so it kind of defeats tonality. So especially in these forms like this one, but sometimes this, we hear those chords throughout the composers of this period. Now, this takes us to our marvelous chart, which I mentioned will become your best friend. So, and I will say, well, this is a listing of every set class that exists. Okay? And, okay, how is this organized? Well, any pitch class set in existence can be boiled down to any one of these set classes. These represent set classes, and each set class contains up to 24 unique pitch class sets. Okay? And so, how is it organized? Well, the first column is the name that Alan Fort, the theorist who put this together, Fort, I think there's an E on the end if I'm recalling correctly. And how they're organized is, you can kind of see it's almost like alphanumeric order. Then the second column is an abstraction of the intervals within the set class, or any pitch class set within that set class. Now you can see right off we've got our 014, which we just talked about, the atonal trichord. We also have this one, 311, which is the 037, 037, which you recognize as the minor triad. However, if I invert the minor triad and I do 037 going down, 037, then I get the major triad, 047, which belongs to the set class 037 or 311. Okay? We know that there are 12 unique major triads and 12 unique minor triads, but this abstract representation, in other words, the set class, is 037. That represents all 24 major and minor triads. Okay, so we have these trichords. There are, 12 trichords. There are quite a few more. Well, there are how many? 29 tetrachords. There are 38 pentachords, 35 hexachords, etc. Now, you may ask, well, why are these nonochords listed across from the trichords and octachords listed across from the tetrachords, etc.? Well, these are what are called complements, and what that means is if I subtract, let's say, the 012 from the set of all 12 pitch classes, what I'm going to be left with is this nonochord. And we could test this out if we had the time, but we're kind of limited in time. So in every case, these are complements. You put this guy together with a transposition of this guy, and you will get all 12 pitch classes, or the set of all 12 pitch classes, the 12-1, which is not listed here. What's interesting is the hexachords, of course, are listed from other hexachords because 12 minus 6 is 6. And some of them don't have anything across from them. That is because they are self-complementary. So the 6, 7, well, let's come up with an example that's familiar. You'll notice that the 635, which is 024, let me play it for you, 024, 6, 8, 10. Of course, that's also called the whole tone scale. Well, the only pitch classes left, if I take these out, are this. the other whole tone scale. Of course, there are only two whole tone scales. So a lot of these hexachords are self-complementary. In other words, if we subtract a pitch class set that belongs to this set class from the set of 12 pitch classes, the remaining pitch classes will form another transposition of that same set class. Okay. Then the third column, the vector, that is the interval class vector. And that tells us how many of each interval class there are. You remember there are 6 interval classes. You know, 1 includes 1 and 11, 2 includes 2 and 10, 3 includes 3 and 9, 4 includes 4 and 8, 5 includes 5 and 7, and 6 just includes 6 because 6 is self-complementary. You notice these are all subtracted from 12. 12 minus 1 is 11, 12 minus 2 is 10, 12 minus 3, etc. 12 being the octave. If we subtract one of these intervals from the octave, then we get this other one. So each interval class contains at least 2 intervals, well, 2 except for 6, plus their compounds. So this vector tells us how many of each interval class is in each set class. Let's take an example let's take the major triad. Why not? 311, 037. And it tells us interval class, there are 0 instances of interval class 1, which is true. There are no minor seconds or major sevenths. There are no major seconds or minor sevenths, so there's 0 in the second position. In the third position, there is an interval class 3 right there. There is an interval class 4. And then there's an interval class 5, which is the perfect fourth and the perfect fifth. Okay? So there's that. If we were to take, let's go down to the next one, which is a 312048. This one has only 3 interval class 4s in it. 048. We know that as the augmented triad, and it has 1, 2, 3. See if we, that's, the interval is 8 or minor 6, but if we invert it, we get interval class 4. So 1, 2, 3, 3 interval class 4s, okay? And you can go through and you'll notice that the vectors are quite revealing. They're quite interesting. There's lots of things we could look at. For instance, we looked at 635, the whole tone scale. One thing you'll notice here is that we have no odd-numbered interval classes. That would be the 1, 3, and 5. Of course, the 1 is the minor second and the major seventh. The 3 is the minor third or the major sixth, and the 5 is the perfect fourth or perfect fifth. We know that those don't exist in the whole tone scale anywhere. But we know there's lots of even-numbered, the interval class 2, which is a major second and a minor seventh. Lots of those. Lots of major thirds and lots of tritones, or 6. We could also look at, what else do we want to look at? Well, look at 735. What is 735? 0, 1, 3, let me see. 0, 1, 3, 5, 6, 8, 10. I'll show you what I'm doing here. 0, 1, 0, 1, 3, 5, 8, 0, 1, 3, 5, 6, 8, 10. Well, of course, that's the white keys of the piano. We could rotate it, move that B up, and we've got our C major. But the normal order of this, of course, starts on B. And so that is what's called our diatonic collection, from which we get our tonal scales, major, natural, minor, and then our modes. Well, that's an interesting one because it's the 735. Look at its vector. There are different numbers of every single interval class. So it's a highly asymmetrical collection. Unlike the whole tone scale, which is super symmetrical, that's indicated by the interval class vector. So there are lots of other uses of it.